issue you have to deal with. So Intel isn't the only company in this game. Their sort of historic competitor is a company called AMD. And AMD was always sort of number two behind Intel. In all the, just like Avis is number two behind Hertz. But the they had a little burst in time when they kind of got out ahead of Intel because Intel had wasted their time on some bad ideas. And they actually were the one that came up with the 64-bit extension to Intel that we use. Right now, though, AMD is not doing very well. Intel sort of realized that it had to get its act together, and it did, and has more or less crushed AMD. And I should mention that they had these ferocious patent suits many years ago, and the result of that was a cross-licensing deal that allows AMD to produce x86 processors too. Now, it's an interesting story behind Intel and 64 bits. They decided to make this radical shift to an architecture that they called IA64 at the time, and it was based on a whole new concept that looked really good on paper, and initial results looked promising. They invested a lot of money in this stuff. They formed a joint operation with Hewlett-Packard on this, and it turned out not to work. It was much too aggressive. It assumed miraculous optimization capabilities by the compiler, and so it was from a technical idea, it was very interesting technology, but in the marketplace it didn't work. And this was sort of a branch off that Intel pursued and felt obligated to keep it up because they'd invested so much in it. And along came AMD and they said, well, we don't have to do this radical shift. We'll just sort of do the obvious thing of adding, making the registers bigger, making things go from 32 to 64 bits. And they came along with that and and were successful. And so Intel kind of had to just sheepishly follow behind AMD on this, but they could because of their cross-licensing deal. So nowadays, as I mentioned, hardware-wise, just about every processor that is in a laptop, in a desktop, even your cell phones of recent generation are all 64-bit processors. So what we'll talk about then, we used to teach IA32, but that's gone. This is the first term where we're skipping it altogether. So we're using what we'll call x86-64. There's various ways this is named, but this is sort of the Linux way of naming it. If you're interested in IA32, there's a document on the web associated with the book called a webaside that goes through at least some of the basics of it. But to really read that, you need to learn the 64-bit because it assumes you kind of already know that. Okay, so let's go in. And I should mention, too, just for general interest, the other major class of processor in common use today are called ARM. So ARM actually is an acronym for Acorn RISC Machine. Now, I just told you what RISC means. It means RISC, Reduced Instruction Set Computer. And acorn means, like, you know, the seed of an oak tree. It was a British company that decided to make its own personal computers in the early days of it. And they said, we're not going to buy those chips from Intel. We're going to make them ourselves. So they designed and manufactured their own chips. Well, as a company, a computer manufacturer, it was a complete bust. But it turned out that they'd come up with a fairly good instruction set that was sufficiently simple that it could be put on chips. And better yet, it could be customized. So ARM is now a company of its own, headquartered in Cambridge, England. And the reason why, part of the reason they're successful, therefore, is because it tends to be a lower power requirements than an x86 machine because it's simpler. But the other is that they don't actually sell processors. They sell companies the rights, the licensing rights to use their designs. And so if you look at like a cell phone processor, the actual ARM processor is a little tiny part of it on the chip. And then they'll have other stuff to make the graphics go better, to improve your phone calls, and so forth. And so they're really selling what intellectual property as opposed to chips. And so we've gotten various inquiries, when are you going to start talking about ARM in your book or your course or something? And we go, it would be another book to write to do justice to ARM. It would be like a whole redo of the thing. And we're not inclined to do that right now. But just so you know, there's sort of two worlds out there. x86 and ARM are the dominant players right now. So let's talk some terminology. And you've probably heard some of these terms before, but let's make it clear. So when we talk about the instructions, the instruction set, that's the target of a compiler to give you a series of instructions that tell the machine exactly what to do. But it turns out that the hardware people have figured out all kinds of clever ways to implement instructions. Some of them are really fast but take a lot of hardware. Some are pretty slow but don't take much hardware at all. And so they managed to create this abstraction that's called the instruction set architecture, which is what the target of a compiler should be, and then let the hardware people figure out how best to implement it. And then so that's a concept actually that came along in the 1960s. So that's even before my time, as far as a computer person. But it's a very important concept in the world of computers. And then what they call the lower level stuff, how it actually gets implemented, is called the microarchitecture. And we will talk very, very little about microarchitecture in this course. And as I mentioned, machine code is sort of a generic term that incorporates both the actual bytes that are executing, as well as the assembly level version of it. And as I mentioned, you can think of from an instruction set point of view, so IA32, x86 64, and what's called Itanium, or this not very successful Intel thing, those are all, in some ways, different instruction set architectures. ARM, actually, similar to Intel, has gone through various different generations. So there's various different generations of its instruction set. So from a programmer, machine-level programmer's perspective, things are a bit different than you see when you write C code. First of all, there's some very visible parts of the machine state that you can examine and test and operate on, and you must, in fact, that you would never understand what those are if you're just thinking in terms of C. So in particular, there's some sort of a program counter. It tells you what address is the instruction that you're going to execute next. Where is that located in memory? And then there's a set of registers which are part of that the programmer actually makes use of. You can think of them as a very small number of memory locations, but rather than giving an address from 0 up to n-1 or something, you actually give them by name specifically. And then there's another sort of state that's just a few bits worth of state that talk about what are the results of some recent instructions where did it produce a value of 0, did it produce a negative or a positive value? And those are used to implement conditional branching, which we'll look at later as we go. And then the other part of it, so that's sort of the processor, and then the other part of it is the memory. And as I mentioned in the one of the first lectures, the memory is, you can think of logically as just an array of bytes. And that's what the machine-level programmer sees. And it's actually kind of a fiction in different ways. As I mentioned before, there's sort of a collaboration between the operating system and the hardware, what they call virtual memory, to make it look like each program running on a processor has its own independent array of bytes that it can access, even though they actually share values within the physical memory itself. And furthermore, you heard the term cache. The idea of a cache is not visible here at all because it just is automatically loaded with recent stuff, And the only thing that will look different is if you re-access that memory, it will go faster than it would if it hadn't been cached. But it's not visible in terms of there's no instructions to manipulate the cache. There's no way you can directly access the cache. So you already see that it's already abstracted. It's got some more details of real hardware, but underneath it, the sort of microarchitecture level has some features built into it that you're not operating on, you're not making use of directly when you write machine level programs. So if you have a program then, say in C, it would typically, on a larger program, it will include multiple files and it will make use of some library code. And so the process of compilation is actually a series of steps that will take what you've written for code, turn it into machine code, combine it with the compiled compiler-generated code for the libraries, and produce finally a file that's your actual executable program. And so that's shown here in this picture, that the first step is to take C and actually generate assembly code from it. And then the next is to run that through an assembler, which takes the text representation of instructions and turns it into the actual byte level representation. We'll look at all this shortly. And then there's a program called a linker, which merges together all the different files for both your individual files, their compiled versions, and for the library code. And then finally, there's even once you run a program, there's actually some libraries that get imported dynamically when the program first begins. So it's a sort of many-layered set of activities. And I'll go through some of these one by one for you. So for example, here's a not very interesting function in terms of doing anything useful, but it sort of demonstrates the basic ideas of compilation. And if I run this through a C compiler, I get something that looks like what's shown on the right. And that's assembly code. And just to give you an idea of what it is, it looks like a sort of strange language the first time you see it. But you'll see those %R something, those are the actual names of registers. Remember I told you there's registers that you give by name. And then those instructions are telling it to do something. Push Q means push something onto a stack. Move means move, copy it from one place to another. Call means to call some procedure. Pop is the counterpart to push. And then ret is exit, return out of this particular function. So you see each of those is an instruction. And it's written in text. But each of those will turn into one actual instruction in the object code representation. So I should tell you that this is actually a slightly cleaned up version of what really happened. So let me show you the reality, because you'll be experiencing that a bit more too. I had this bigger before. Let me make it bigger. Blow this up so that you can see it. Can you see it in the back there? Bigger? Better? And let me get the other one. No, that's not what I want. And I've already logged into a fish machine to get here. So this is a file then. You see it's called sum.c. And I'll mention that all of these programs are available. You can see the whole well, /AFS is my own personal, and all that first stuff is my own personal links. But once you get to the class web page, www/code/ and then it's all given by which particular lecture it is. I think these are linked on the home page too. And you can see various files there that are used for the demonstration. The C files are obviously the programs that we typed in, and then ones that have an S at the end, that's assembly code. One that are D are what's called disassembly. So anyways, if I say GCC minus O2 minus OG minus S capital sum.c, that what I did was just tell the compiler to take the C code and turn it into assembly code. So when you invoke GCC, you're actually invoking it not just one program, but a whole sequence of programs that do various stages of the compilation. And by giving it this minus capital S switch, I'm saying stop, just do the first part, C to assembly code. And the minus O little g is a specification of what kind of optimization I want the compiler to do. So if you don't say anything, if you just don't give any directive, it will generate completely unoptimized code, and it's actually very hard to read that code. It's very tedious the way it works. If you say minus O1, which is what you used to do to turn on the optimizer, it turns out that as GCC, as they've gotten more advanced, it does a lot of optimizations now that, for the purpose of this course, make the code pretty hard to understand. So it just, with one of the most recent generations of GCC, came out with this level called G for debugging. That's a nice, for this course, purpose of this course, a nice level that it sort of does the obvious kind of optimizations to make the code readable without being sort of extravagant and trying to rewrite your whole program in a way that would make it a lot different and hopefully more efficient. So that's what we'll use in this course. It only exists in the recent versions of GCC. It's non-standard across other compilers. Question?
Is that a 0 or like an
No, it's an O, capital O. It stands for optimize. So what that command just did was produce a file called sum.s. So let me show you what sum.s is, and let me show you the function sumStore. Can you see that then? Okay. So this is the code. It says sumStore, and then you'll recognize those instructions I mentioned before: the push, the move, the call, the mush, the move, the pop, and the ret. But you also see other junk there that we edited out for the presentation, and even in the book it got edited out. And the reason is these are various directives that aren't really directly part of the code itself. The fact they start with a period is an indication that these aren't actually instructions. There's something else. And they all are related to the information that needs to be fed to a debugger for it to be able to locate various parts of the program, and some information for the linker to tell it that this is a globally defined function, and various other things that you don't really need to at least think about initially. So we sort of take those out of the program just to make them more readable. But if you ever do this yourself, you'll find this crud in there, and we don't want you to get like, oh my gosh, this wasn't in the book, I don't know what to do with it. So let's go back. The other thing is people are learning on Data Lab is Shark versus non-Shark. It makes a difference. And even like, this is a Mac computer and I've got GCC installed, and it generates its Intel processor in there, but it's not directly compatible with Linux code. So it's pretty important for this course. We're saying just stick with the Shark machines for everything you do. So what are some characteristics then of assembly code, especially how do they differ from C? Well, first of all, there's a number of different sort of integer data types of size 1, 2, 4, and 8 bytes. In integer data types, they don't distinguish signed versus unsigned in how it gets stored. And even an address or a pointer is just stored as a number in a computer and doesn't have any special significance to it. A floating point is handled in a very different way, on the other hand, with a different set of registers that I think we'll talk about very briefly in one of the later lectures. The program itself is in x86, it's just a series of bytes, and I'll show you some examples of those. And things like arrays and structs and things that you think of as fundamental data types don't exist at the machine level. They're sort of constructed artificially by the compiler. And later in the course, in these lectures, we'll cross over into how that's actually done as well. So some of the things you know about in C exist here, and some of them are sort of have to be built up in layers on top of the assembly level program. So the other thing about assembly level programming is each instruction is very, very limited in what it can do. It can move data from a register to memory, or it can do an addition or a multiplication or something like that, but it can really basically only do one thing. And so you have to write a whole, if you were writing it by hand, you'd have to write a whole series of instructions to get anything done. And that's part of the reason why it's really much better to let the compiler do that. And we'll also see there's sort of how things like do loops, while loops, conditionals, switch statements, those are all built up on top of some other lower level features in the instructions. So for this function, sum store, actually it gets encoded by a total of 14 bytes. And so one thing about x86 is some instructions are as short as 1 byte, but others can be as long as 15 bytes in the encoding. And like I said, each instruction really typically only does one thing. So for example, in C, if you say star dest equals t, what that will typically, and not always, but the sort of way to think about that at the machine level is it's t, or some local value, would be typically stored in a register. And as you know in C, if you put star in front of it, you want it referenced as a pointer. And if that reference is on the left, you want to store a number, a value, at that place where you're pointing to. So what would typically happen is dest, the actual pointer value, would also be stored in a register. Here it's in register RBX. And I use a move instruction to say, take the value from one register, which is called RAX here, and store it in the memory location that's specified by another register. So you see the idea. We'll go into more detail about all these register names and what the parentheses mean, but you get the rough idea that a move instruction is saying, can refer to either a register or a memory location. And the actual object code representation of this is just 3 bytes, where the first byte tells it that it, and we won't even talk much in this course about how the instructions are encoded. Won't generally let programs do that for us. But in this case, it only takes 3 bytes to write that particular instruction. So how can we know that kind of stuff? How can we figure out that level of detail? Well, there's some really useful tools that let you examine machine code even if you don't have a copy of the original C file or even the assembly code file ahead of time. And there's one called a disassembler. So an assembler goes from this text version of instructions to a byte level representation. And a disassembler just reverses that. It says, here's a series of bytes. And I, the disassembler, know that this particular byte sequence is a move instruction. And so it will now print out on the screen to say, oh, that was a move instruction. And so it basically reverse engineers from the object code back to the assembly code, or something sort of like the assembly code. You'll see it lost, it's very slightly different. One thing also to notice I should mention about assembly code is all those, all the names I used, all the names of variables are completely lost at the assembly code level, or at the machine code level. Things are they're in registers, they're somewhere in memory. The program has no understanding of your original source code at that level. And so the disassembled is just a way to go backward. And you can do that yourself, and you'll find that useful in various contexts to do that yourself. Things kind of monkeying around maybe. So if I compile the sum program, so if I do the more standard thing you do in using a compiler, you say, run the compiler, give it some optimization, tell it what the source files are, and tell it where to put the final executable code. And I'm terribly clever. I call the function sum. And so sum is a binary file of 8,663 bytes. You'll see off on the left it's marked as executable. And it actually works. I can add numbers together with it. So that's your sort of standard executable program. Excuse me. And if I run a program called object dump and ask it to disassemble, it can do various things. It will spit out a disassembled version of the program, and it will fly by on the screen. But if I redirect that to some file, which I already did, I'll remove the old one. And now I look at that, you'll see that it has what I described as is the disassembled representation of the program, including some files that you didn't, some functions that you didn't write. It has ones that are sort of the low-level functions that are used in the initial startup of a program called init. Oops. But here, somewhere in the middle of it, you'll see, lo and behold, is that program, that function sumStore that got compiled. And you can see that what it did was it took this 14 bytes from the original, the object code, and it picked those apart and came back with what instructions those bytes encode. So for example, the push instruction only takes a single byte. The move, as you saw before, takes 3 bytes. This call, because it has to give a location of where to call, is a 5-byte instruction, and so forth. But again, the disassembler didn't have access to the source code. It didn't have access even to the assembly code. It figured this out just by the bytes in the actual object code file. So this is the way, if you ever want to know actually the byte level encoding, this is how you figure it out, is to run a program, run it through an assembler, get object code, and then come back out with it. There's another way you can do it using the debugging program, which you'll get to know very well in the next lab you're going to do. And it's called GDB. And GDB is a very powerful debugging program that you can examine, step through, and operate on programs in. And again, you can, if the source code for it's available, it will make use of it. But it also can be used on programs for which there's no source available. But one of the features is the ability to disassemble functions in there. So if I say disassemble sum store, it'll come back with something that looks a lot like what you saw from object dump. A listing of the instructions. And here it just shows in hex what the addresses of those different instructions are. It doesn't show the byte level encoding. So my point here is there's various tools that let you look at a program even if its actual representation is a binary file that you don't want to examine directly. Let me just plug this in. So what this slide shows is what I just showed you on the screen, which is what the object dump program produces for this function. And this is a version showing what GDB would show you for it. And with GDB, if you want to actually get the bytes out, you can do that. You can basically, for any address, you can just give an address and tell it to display some number of bytes. And so this rather cryptic command to GDB says examine 14 bytes in hex format, starting at the address of the function sumStore. And it produced something that looks like what you see on the left. In fact, disassembly is a tool that can be used as part of any reverse engineering tools. And I used to demo this by showing a disassembly of the windows of Microsoft Word. I had a PC back then, not a Mac. But some people, and you know our slides are online, and so we got some nasty grams from people saying, you know, you're violating the Microsoft end user license agreement when you do that, because you're supposed to, you don't know this, but remember all those click through I agree things that you never read? One of them is, I agree not to try to reverse engineer any Microsoft product. So this would technically, so I've sort of just for modesty, I blanked this out. But you can actually do it. If you can find where the file is, it's sort of obscure where the actual executable files of an application are. My point is that Word, like any other application you run, is just an executable file, and that executable file is just a bunch of bytes that encode instructions. Okay, so let's go a little bit further into this assembly level programming business. So I keep talking about registers. And x86-64 has this totally quirky set of registers, and it's a reflection again of this sort of evolutionary history to it. But you'll see that there's 16 registers that you can use to hold integers and pointers. And some of them have these sort of alphabetic names, and some of them have numeric names. I'll show you why in a minute. And also for each register, if you use the sort of %R name of it, you'll get 64 bits. But if you use the %E version of it, you'll get 32 bits. And what you'll find in programs that manipulate long ints, you'll see the use of R. And if they're just ints, 32-bit things, you'll see code saying %E. So you'll see both of these show up. And it's fairly important to remember that the %E version is just the low order 32 bits of a larger %R entity. And in fact, it goes beyond that. You can also reference the lower order 16 bits and the lower order 1 byte, 2 bytes and 1 byte within each of these registers as well. But again, think of these as like named locations where you can store values and you can retrieve values from them. And you have to, I'm sort of personifying machine level programming here, not you personally. We'll actually have to explicitly name those registers for the most part to say where things should go, where they should come out of. It's not like a memory where you just give a number to tell where to look for. You could compute a number. They're actually, each one is identified separately. So just as a little bit of history, with IA32, so back, we just talked about there being 8 registers, all the %E versions. And one of the changes that went from IA32 to x86-64 was to double the number of registers. And by the way, this is a really helpful thing because it was very frustrating how few registers there were in the old IA32 machines. And then as I mentioned, you could actually, in the old machine, refer to the low order 16 bytes of these registers, and that was a legacy from the 8086 days. And within the first 4, you could even refer to the individual 2 low order bytes in those. So nowadays, you can actually get to the low order byte of all of them, and we just sort of, that's covered in the book actually. We don't talk about how you can get to these bytes because that's really a legacy from back before the 8086 was one called the 8080, which was an 8-byte machine. So anyways, you can see then how you got from this kind of weird state of affairs to the even weirder state that we are in today, where some of them have names and some of them have numbers. And those names, by the way, had a reason back in ancient days. They had very specific purposes, and so they were given names that sort of reflected those purposes. But that all went away years and years ago, and so now these names are just legacy names that have nothing to do with their purpose. Now I should mention there's one special register nowadays, as shown in pink here, and that's called the stack pointer. And that register you don't just use any old way you please. That has a very specific purpose. And all the other registers, there's some that are slightly different than the other, but for the most part, they're all usable for holding program data. Back in the IA32 days, there was a register called the base pointer that also got used for procedures, but that no longer gets used anymore either, at least not usually. So anyways, I don't want to spend a lot of time on historic legacy stuff and have you memorize what feature was added in what model of processor, but just in case you're wondering why there's these weird names for these things, just so you appreciate the fact that this is a legacy thing. Okay, so now we can think of it then that there's 8 registers with names and there's 8 registers that are indicated by some number. And let's look at some of the instructions that operate on those registers. And there's sort of 3 different, the move instruction in x86 is actually, can do a lot of things. Because it can take different types of information, or what they call operands. So the source is where you're copying from the source to the destination. The source can be some what's called immediate. It's actually a number that's baked into the program that you want to copy into some other location. A register we've talked about one of these specially named memory locations. And memory is the array of bytes that you have to specify what's the address that you're either reading from if it's the source, or you're writing to if it's the destination. And so the move instruction gives you all these possibilities. An immediate value can be written to a register or directly to memory. A register value can be copied to another register or written to memory. Or you can take a value from memory, read it from memory, and copy it to a register. So if you think of, wait, shouldn't there be 9 different combinations here? Well, no, because it doesn't make sense to have an immediate value as a destination, right? It's a constant. And also, just for sort of the sake of convenience of the hardware designers, it doesn't let you directly copy from one memory location to another. What you have to do is use 2 instructions. One to copy from memory, to read it from memory, copy it to a register. And a second to take that value in the register and write it to memory. So that's why there's only 5 possibilities. And so each of these actual 5 combinations you'll see in some form or another. So for example, if I take a constant value and copy it to a register, it's a little like, you can think of registers as sort of the temporary data that you're operating on right now. So it's a way of sort of assigning a constant value to a temporary. Similarly, if you have a memory as your destination, it's like storing a constant value in memory somewhere. If you're copying from one register to another, it's sort of like copying one temporary value to another one. Register to memory, it's as if it's sort of like storing to an address, so a pointer dereference where the pointer is on the left side, the dereference. And memory to register is the opposite. It's you're reading from some location into a temporary position. So these, you'll see all 5 versions get used in some form or another. So now let's talk about how we write these pointers, how we specify either a source or a destination for a memory reference. And you already saw one version of this, in fact, in some of the code. When you put the name of a register in parentheses, that's just saying use this register, whatever is in that, that's an address. And use that address to reference some memory location. And so you'll see something like this is the equivalent of dereferencing a pointer and putting it in a temporary. You're also allowed to do a little bit of arithmetic to derive an address from some collection of registers and other constant values. So if you see a number, it's called the displacement, d. In front of this parentheses, it means to offset, not use the address that's in the register, but add or subtract some number from it to get an address that's just slightly off of it by some fixed amount. And that we'll see is fairly useful for accessing different data structures. So here's an example of a very simple function that we can understand everything about it already because we know what the move instruction does. And that's the sort of classic swapping of 2 values that are stored in memory. So my arguments are 2 pointers called xp and yp. And I'm going to dereference those pointers. I'm going to read from memory into registers. And then I'm going to copy back to memory, but reversing the 2 destinations. And so, as you can imagine, it lines up to be 4 move instructions that correspond to these 4 references. And the final one, we'll learn more about functions and how they're called, but just think of the ret as it returns from wherever the calling position was. And so let's look at more detail at the actual code then. And so it turns out with the 64, x86-64, the arguments always come in some specific registers. And the ones to remember for today is RDI will be the first argument register and RSI will be the second argument register. There can be up to 6 of these, and we'll go into more of that later. So those two registers represent the values of XP and YP. Those are set before the function is actually begins executing. That's set by the part of the code that calls this function. And those will be pointers. So what they are is they contain addresses that specify locations in memory. And then within the code, the compiler just came up with its own ideas of how to use different registers for temporary data by whatever what's known as the register allocation algorithm it uses. And we don't really care. We just want to, what we'll want to do is figure out what it's doing. And we'll see that a register RAX is being used to hold the value T0 and RDX the value T1. So let's get actually concrete here. And this is very detailed, but I think it's important that you understand sort of, you can almost simulate the execution of some instructions by yourself. You're going to really have to know this stuff. So what each of these instructions is doing and how it works, and really have that wired into you pretty well. So let's make up an example. Let's imagine that the two addresses that are used for these two pointers are in hex 120 and 100. By the way, those would not be typical addresses. They're way too small a number, but it's much easier to use them as an illustration. And let's suppose that one of them held the value 1, 2, 3, and the other 4, 5, 6. So the first instruction says, use RDI as an address, copy from that memory location, and store the result in register RAX. So RDI is 120. I'll read from that address. I'll read the value 123 and store it in register RAX. These are all, by the way, 8-byte values. And I'm just sort of glossing over that part of it. But the Q refers to what in Intel terminology is a quad word. A word, because it goes back to the 8086, is 16 bits, 2 bytes. A long word is 32 bits, and a quad word is 64 bits. That's just their terminology, and we're stuck with it. Okay, so that one instruction had that effect. The second instruction does the same thing, but using RSI, which holds 100 as an address, and so it copies 456 into RDX. And then the third instruction is writing back to memory. So its source is register RDX. The destination has the address of RDI, which is 120. And it's storing that back in memory. And finally, this fourth instruction does the other part of the write. So you see these 4 instructions, 2 read from memory into registers, 2 of them wrote from registers back to memory, and that's the whole function. And you can see this move instruction is doing all the work here. So we've shown that example just showed this very simple memory referencing that's designated by the parentheses. And as I mentioned, you can do a version where you put a displacement there too. And in fact, there's a much more elaborate form, and we'll see that this is useful for implementing array references, where there can be actually 2 registers involved. And there can be a displacement, which is a constant offset, and a scale factor, which will be 1, 2, 4, or 8. And the general idea of it is to take our register that I'm referring to as R sub I, that's known as an index register. You multiply it by the scale factor. You add the value of RB, register RB, and you also add the constant displacement. And these have RB refers to base, Ri is index, and S is scale. And it turns out this will be the sort of natural way to implement array referencing. It will make a lot more sense when we talk about arrays. But basically, you can think of as if this is an array index, I have to typically scale it by however many bytes my data type is. So if it's an int, I have to scale it by 4. If it's a long, I have to scale it by 8. So that's where these scale factors will come in. And basically, the format in the assembly code lets you eliminate some of these fields if they're not being used. So you'll see, and we already saw the single parentheses is sort of a reduced version of this form. So let's just do some examples of these address computations. And let's imagine that register RDX holds hex F with 3 zeros, and RCX holds 1 with 2 zeros. So if I, rather than doing it one at a time, you can see each of these. I'm taking RDX, which is F with 3 zeros, adding 8, and so that's F008. Here I'm adding together registers RDX and RCX, and that gives me F100. I'm doing the same here, except that I'm scaling RCX by 4. So 4 times 100 is 400, and I'm adding that to F. And here I'm taking RDX, which is F0 with 3 zeros. If I double that, I get 1E with 3 zeros. If you think about shifting an F to the left 1, you get a 1, and then it goes 1, 1, 1, 0, and that's an E. Okay? And then I'm adding this displacement of 8, 0 to it. So the point of this is all of this is arithmetic. It's all using whatever's in the register, and there's some rules for how you combine this and get an address, and then that's being used to either read or write some memory location. Okay, so now let's, as a final part of today, go through some arithmetic. And one of the things that will be sure to confuse you and drive you crazy and make you be sending email to the staff for explanation is an instruction called load effective address. And the reason is its purpose in life is to do basically the ampersand operation of C, to compute an address based on some whatever you want to compute an address from. But it also turns out to be a pretty handy way to do arithmetic, and the C compiler likes to use it. So in particular, it looks, the format of it looks like a move instruction. There's a source and a destination, but the destination has to be a register. And the source will be one of these memory references. So it looks like a move instruction. It looks like you're doing some address computation, then you're reading from memory and storing it to a register. But what it actually does is it does that address computation, and then it actually writes that address, not the memory value, but the value that got computed directly to the register, which is what you want to do. Here, remember, the ampersand operation is give me the address of some place. Give me a pointer that designates some location. So for example, this is fairly typical in C code. If you say multiply x by 12, it'll turn it into an address computation, and this is just a clever way to compute 3 times RDI. It adds RDI plus 2 times RDI, so that's 3 times RDI, and stores it in RAX. And then salq means shift left by 2, and so you remember shifting left by 2 is like multiplying by 4. So the first value computed 3 times x. I shift that left 4 by 2 positions, and I have 12 times x. So that's a very special, the LEA, but you'll see it all over the place, so you need to be ready for it. These other ones look more like what you'd expect for arithmetic instructions. They have names like add and subtract and multiply and so forth. And they all have the same general format, that they have two arguments. And what's called the destination is actually also a source. It's a little like in C, if you say x plus equals y. It's saying take the value of x, add the value of y, and then store the result in x. And now the destination is like that. The other thing that's weird is that the operands are in the inverse order from where you'd expect them to be. So the source comes first and the destination comes last. And that's important to remember. And other thing, you'll see that there's nothing special here, whether it's except that this is a arithmetic shift and this is a logical shift, of whether it's a signed or unsigned value, because you remember the bit level behavior of these two instructions is the same. And then there's a series of instructions that are used that are just take one operand: increment, decrement, negate, and not. Not is like the tilde operation in C, not the exclamation mark. So those are the basic instructions. And again, now we can actually look at some programs and understand them. And here's one that just does a bunch of junk of arithmetic instructions. And it converts into the following assembly code. And you see it's using this LEA instruction multiple times to do addition in various forms. And it also has shifting, and it has multiplication. You saw in the original code, I just have addition and multiplication. Here I have various instructions. I only have one multiply here, whereas I had two there. So the compiler is sort of scrambling things around, trying to find clever ways to implement what you're asking for using less expensive, less time-consuming instructions. And if you sort of go through this code carefully, what you'll find is that this instruction here corresponds to this computation of T1. It's adding two values and giving it a new name. It's putting in RAX. Similarly, this one is adding Z to T1 and storing it back in RAX. The x plus 4 doesn't show up directly here. It turns out what it does is it jumps right ahead to here, and to multiply y by 48, it does it by first computing 3y, like we saw before, and computing, shifting that left by 4, because 3 times 16 is 48. And then the 4 here that's in x plus 4 actually shows up here. It just uses the displacement field of this computation to add 4 to some other values. And so this is labeled, and these comments show how these correspond to the program, and these registers show it. So the important thing to get from here, you will want to actually go back through this and make sure you believe that the comments are correct. But it's very important for you to figure out this LEA instruction. Otherwise, you're just going to be hopelessly confused. And it's also important to understand that the code that gets generated will correctly implement your C function, but it might not exactly replicate at a low level the exact sequence of operations you specified at a high level. So that will, just to summarize then, you've already gotten a glimpse then of what this very odd world of machine programming is and how different it is from C code already. So you've already seen that x86 is weird. Like I said, it's English. It's not Latin. It's not well designed. And but you just got to deal with that. So that's your beginning to machine level programming. Thanks a lot.